Welcome students to our fourth part of quadratic functions, section 2.3. Here we will explore the quadratic formula. First off, we have to understand what it means to solve a quadratic equation, or just simply a quadratic. Solving a quadratic means finding where, if at all, our quadratic function hits the x-axis. Solutions are x-intercepts. The next question we want to ask is, how can we solve a quadratic equation? In order to solve a quadratic equation, we have a couple tools in our toolbox. The first one we have used a few times. One way that we can solve is if our quadratic equation is factorable, we can factor and then set each factor to 0. So factor and set to 0. Another method that we're not going to hit on just yet is called completing the square, and we can use that. That's usually the least popular method for students. But the one that always works, unlike factoring, the one that always works is using the quadratic formula. And this one, if you forget factoring, if you can't complete the square, using the quadratic formula will always give you answers to your quadratic, no matter what the quadratic looks like. If it's pretty and factorable, if it's really ugly, whatever types of solutions it has, the quadratic formula has got your back. All right, this handy-dandy equation is right here, so make sure that you have this written down. Up here it says, for our quadratic, ax squared plus bx plus c equals 0. This is telling us that in order to use the quadratic formula, our quadratic needs to be equal to 0. That's step one. So if it's not equal to 0, we must make it equal to 0, and then we can properly identify a, b, and c. And of course, a cannot be 0, because then we wouldn't have a quadratic. There'd be no x squared. Here is the formula. It's x equals because we are finding the x values, the x-intercepts. This is the formula right here. For these first two problems, I picked factorable quadratics, and I'm going to show you how we can both factor and use the quadratic formula to solve them. And then we will double check our work on Desmos. So what I'm going to first do is I'm going to first factor this. I'm not using the quadratic formula first. I'm going to factor it and show you that factoring is a pretty easy method, and then that we can also use the quadratic formula to get the same answers. All right, factoring to solve, this one's pretty easy to factor. We'll get x minus 5 and x plus 3. Since negative 5 and positive 3 will multiply to give us negative 15, and negative 5 and positive 3 will add to give us negative 2. If you're unsure if you factored correctly, you can always FOIL or multiply back out, and you should get back to the equation. Of course, we still have equals 0. Therefore, we've only factored, we haven't solved yet. We need to set each one of these factors equal to 0 in order to find our solutions. And we'll add 5 here to get that one solution is 5. We'll subtract 3 here to get that our other solution is negative 3. That means that this parabola, this quadratic, the graph of this quadratic, hits the x-axis at negative 3 and 5. All right, now the main course. Let's use the quadratic formula. All right, here is our quadratic formula. We first need to make sure that we're equal to 0. We are. Then we can identify a, b, and c. Let's write that off to the side. So we'll have that a is 1, that's a number in front of x squared. B is negative 2, the number in front of our x. And c, the constant, is negative 15. Negatives do matter, so be careful with that. All right, now we can plug in. We're going to have the opposite of b. So we'll have the opposite of negative 2 to begin. So we'll have 2. Then we have a plus or minus, big square root. And what goes under that square root is I'm first just going to square b. I'm just going to do that in my head. So we're going to square negative 2. Whatever b is, when you square it, it's always positive. So I'm just going to write a 4 here. Then minus 4 times our a value of 1 times our c value of negative 15. All over 2 times a is 1. As we keep going, we want to get what's under the square root here. This is called the discriminant. And these three numbers are all being multiplied here. So we're multiplying a -4, yes, I'm calling this a -4, a 1, and a -15. We have two negatives that are being multiplied. That means I'm going to get a positive number here when I multiply all three of these numbers. I might as well think about it as 4 times 1 times 15, since those two negatives will multiply out to be a positive. So that will end up being a positive 60. So we'll have 4 plus 60 under there, all over 2. So we have 2 plus or minus the square root of 64 all over 2. 64 is a perfect square. It's 8. So we have 2 plus or minus 8 all over 2. Now, because this number's not in a square root anymore, we're going to use the plus or minus to find our two answers. I'm going to do 1 plus and 1 minus. So this one's going to use the plus sign. We'll have 2 plus 8 all over 2, and we'll have 2 minus 8 all over 2. All right, 2 plus 8 is 10. 10 over 2 is 5. 2 minus 8 is -6. All over 2 is -3. So our two solutions, in both cases we found, which we should, it's the same problem, are 5 and -3. All right, I have graphed this on Desmos just quickly so we can see that our graph, our parabola rather, hits the x-axis at -3, and it also hits the x-axis at 5. So those are our two solutions that we found, and visually on a graph, the solutions are the x-intercepts. So there they are right there. Now, why do we care about x-intercepts so much in math? Like, why do we need to solve to find that all the time? Well, if you think about, just for one example, like a business application, right? If you're graphing, let's say, profit, you care when your profit dips from positive values up here to negative, or from negative up to positive, right? We care about that. And the great divide in math between positive and negative numbers is 0. So we care when our graph hits 0. That happens to be on the x-axis. All right, let's take a look at this next problem. We see that we do not have it equal to 0, and in order to factor or to solve or to use the quadratic formula, we do need to have our quadratic equal to 0. So I'm going to add 32. So we'll end up having 2x squared plus 16x plus 32 equals 0. We added 32 to both sides. So now we have our quadratic equation equal to 0. Let's see what we can do. We see that there is a GCF of 2, so I'm going to factor out a 2 just to make this an easier problem to work with. We'll be left with x squared plus 8x plus 16 equals 0. So now, yes, there's a 2 out front, but the quadratic that's in parentheses is what we care about. So let's see if this is factorable. Are there, in fact, two numbers that multiply to 16 that add up to 8? As a matter of fact, there are. So the 2 will stay out front, and we'll be left with x plus 4, x plus 4. It's actually a perfect square trinomial because the x plus 4, we could have just written it as x plus 4 squared. It's something times itself gives us this. All right, so this was a factorable quadratic here, right here. And now we're going to set each factor to 0. So I'm going to set 2 equal to 0, that's a factor. I'm going to set x plus 4 to 0. And I'm going to set x plus 4 to 0 again. We have 3 factors. This does not provide us any solutions. This one will provide us a solution of -4, and so will this one. Instead of writing a solution twice, we'll just write it one time. And we will get into something called multiplicity later on in the year. It just means how many times something occurs. So we'd say that the solution to this quadratic is -4 with multiplicity 2. All right, so that was factoring. Let's now use the quadratic formula to solve. What I'm actually going to do is from this point right here, we factored it pretty nicely. I'm going to start with this point right here, this factored version instead of the original. Now, I did this problem specifically with a GCF out front because if we went here, you would see that our A, B, and C values would be 2, 16, and 32. Those are large values. If we factor this 2 out, like we did, This is the quadratic we would use, and so our a is 1, our b is only 8, and our c is 16. Much easier doing it algebraically. So whether or not you factor the 2 out or not, you'll have different a, b, and c values for the quadratic formula, and you'll end up with the same answers in the end, but it's much easier if you factor out a GCF from the start. So I'm going to use a is 1, b is 8, c is 16. All right, then we'll use our quadratic formula. We start with the opposite of b, so the opposite of 8 will be -8, plus or minus. We square b, so we'll square 8 and get 64, minus 4 times our a value of 1 times our c value of 16, all over 2 times our a value of 1. All right, we want to simplify what's under the square root first. What's under here is called the discriminant. I'm going to have a 64. And then again, we're multiplying 3 numbers, a -4, a +1, and a +16. So we have an odd number of negatives, negative times positive times positive. So our answer is going to be negative. And 4 times 16 is 64, all over 2. We end up with a discriminant of, discriminant of 0. So we have the square root of 0. Well, the square root of 0 is 0. We're left with just -8 plus or minus nothing all over 2. I don't need to write plus or minus 0. It doesn't do anything for us mathematically. -8 divided by 2 is -4. That's showing us that we did, in fact, only have one solution. Yes, it occurs twice, but our one solution is -4. Okay, let's take a look at problem number 3. We want to solve this quadratic. We do have to first make sure we get to 0, so I'm going to add 2x to both sides, and I'll put it where it belongs in between the x squared term and the constant term, because we need it to be equal to 0. Now, this one does not happen to be factorable. 2 times -7 is -14. There's not two numbers that multiply to -14 that add up to 2. So this is not a factorable quadratic. We have to use the quadratic formula. So we will begin. Our a is 2, our b is 2, and our c is -7. Okay? Then we want to do the opposite of b, plus or minus 2 squared, minus 4 times 2 times -7, all over 2 times 2, which is a. As we go, we want to simplify the discriminant, so we'll have 4. Note that there's 2 negative symbols. A negative times a negative is a positive. So we'll have 4 times 2, which is 8, times 7, which is 56, all over 4. We'll have -2 plus or minus the square root of 60, all over 4. Now, this is a slightly different example because this value right here is not a perfect square. The square root of 60 is an irrational number. In order to get exact values, though, we are going to break down this radical. So we have -2 plus or minus, and we want to break down the square root of 60, which I've changed to orange here. What is the biggest perfect square factor of 60? What number fits into 60 perfectly and is also a perfect square? The biggest one is 4. And so we can write the square root of 60 as the square root of 4 times the square root of 15, since 4 times 15 gets us back to 60, and root 4 times root 15 is the same as root 60. All right, still all over 4. So again, in orange here, we're breaking down the square root of 60. Since 60 is not a perfect square, we have to break down the radical. The square root of 4 is a plain old 2. So we will have -2 plus or minus, and then the square root of 4 will be replaced with a 2. The root 15 stays, and then that's all over 4. Now, if we can simplify these 3 values right here, these values that make a triangle, all the ones outside the root, go ahead. They can all be divided by 2. And so when we divide those all by 2, we'll have -1 plus or minus 1 root 15 all over 2. And those are our 2 answers. This problem was not factorable. Look at the type of answer we got. It's real, but it's irrational. That means that this quadratic hits the x-axis 2 times. Once with the plus sign, once using the negative sign. But where it hits the x-axis is messy. It's not a nice, easy integer that we can see. All right, just to show you, I graphed our quadratic once it was equal to 0, and these were the two solutions we got. I broke them apart. Oops, I accidentally put the plus or minus there. I meant to just put the plus sign. Whoops. So the -1 plus root 15 all over 2 and -1 minus root 15 all over 2 are our two solutions. In my calculator, I just found them. I used the approximation. And 1.44 is about here, and -2.44 is about here. So these are the two spots approximately where a graph hits the x-axis. The reason we don't write our final answers in decimal notation is because this is an approximation. These are the exact ways to write our two answers. In conclusion, the quadratic formula is a foolproof way that allows us to find the solutions to any quadratic equation. So long as it's equal to 0, we can use it to find the spots or spot where our quadratic hits the x-axis.